Hello everyone, my name is Sheikh Ufa from second year ECC. Introduction to Boolean laws and Boolean theorems. Boolean algebra introduction. Boolean algebra is a branch of algebra that deals with binary values 0 and 1. Applications of this is digital circuits, computer science and logical theory. Basic operations. Here are three basic operations. They are AND gate, OR gate and NOT gate. These are the fundamental operations. Truth gate, AND or not. Truth tables show how logical operations work. For example, A, B, and A dot B and A plus B, A complement. Here are the examples for that we can show. And Boolean algebra laws. Here are three laws. They are commutative law, associative law, and distributive law. In these commutative law is A plus B is equals to B plus A, and A dot B is equals to B dot A. And the second one is associative law. A plus B whole plus C is equals to A plus B plus C. And second is A dot B dot C is equals to A dot into B dot C. Distributive law. A into B plus C is equals to A into B plus A into C. And the second is A plus B into C is equals to A plus B into A plus C. Identity law. A plus 0 is equals to A. And the next one is A into 1 is equals to A. Null laws. A plus 1 is equals to 1 and A dot 0 is equals to 0. And idempotent law. A plus A is equals to A. Here sum of two A's is equals to A. And product of two A's is equals to A. Complement law. A plus A complement is equals to 1. And the next one is A into A complement is equals to 0. And here is double negation law. A complement whole complement is equals to A. The next one is De Morgan's theorem. A into B whole complement is equals to A complement plus B complement. And the next one is A plus B whole complement is equals to A complement into B complement. Here are some logic gate diagrams. For example, AND gate is a multiplies inputs, and OR gate has add inputs, and NOT gate has inverts inputs. For example, the basic logic operations are the use of switches, closed and open electrical paths, and light bulbs to illustrate the idea of logic variables and functions is convenient because of their familiarity and simplicity. The logic of the logic concepts that have been introduced are equally applicable to the electronic circuits used to process information in digital computers. With the help of transistors, it is possible to design simple electronic circuits that perform logical operations, such as AND gate, OR gate, and NOT gate, and XOR gate. It is customary to use the name gates of these logic circuits. The first one is NOT gate. It is an inverter gate. For example, we give input as X and we get the output as Y. We can see the truth table. Input is X and output is Y. We can give the input as 0, we get the output as 1. We get the input as 1 and we get the output as 0. NOT gate is a simple in single out logical device where the output will always the complementary form of the input. This means that the output is 0 for the input equals to 1 and vice versa, as indicated in the table. This is symbolically written as y equals to x complement. And AND gate. Here we have two inputs I1 and I2. The output is y. Here we can see the truth table as two inputs I1 and I2 and the output is y. For example, we give input as 0 and 0. We get the output as 0. And we get inputs as 0 and 1. We get output as 0. and we get the inputs as 1 0 and we get the output as 0, and we have inputs 1 1 and we have the output as 1. AND gate is a basic gate with multiple inputs and a simple output. This gate has its output high only if all the inputs are 1, failing with which the output will be 0 as shown by the truth tables. The logical expression considering to this gate is given as y is equals to I1 into I2. And the third is OR gate. OR is a type of basic gate with multiple input, single output characteristics. Here the output is 0 only if all of its input bits are 0. The logical expression for the OR gate is given as y is equals to I1 plus I2. I1 and I2 are the inputs and y is the output. Here we can show the diagram as in the figure. Here I1 and I2 are the inputs and y is the output. In these, the truth table shown as I1 and I2 is given as 0 and 0 and output y is 0. Here input I1 is 0 and I2 is 1. Then the output is equals to 1. Here next I1 is 1 and I2 is 0. The output is also 1. And the final I1 is 1 and I2 is 1. The output is equals to 1. This is the OR gate. And these are the universal gates. There are two universal gates. They are NAND gate and NOR gate. First we can see that NAND gate. In NAND gate, the inputs are I1 and I2. Output is Y. This can be written as input I1 and I2. In these intermediate output in the middle and output is Y. The truth table is inputs I1 and I2, intermediate output is M and output is Y. Here we can show the truth table, and NAND gate is a logical equivalent to AND gate followed by a NOT gate. The truth table for these is as shown in the figure, that the output of NAND gate is low only if all its inputs are high. The output of NAND gate is the negated output of the AND gate represented by the intermediate output M, as shown in the above truth table. Logical expression for the NAND gate is given by y is equals to I1 into I2 whole complement. This is the NAND gate. And the next one is NOR gate. NOR gate can be represented as shown in the figure. I1 and I2 are the inputs and y is the output. Here also we can show the intermediate output. The truth table is I1 and I2 are the inputs and intermediate output is M, the output is Y. Here the truth table is NOR gate is the result of combining NOT gate with an OR gate. Thus its output is the negation of OR gate output, which implies that it has only output only if all of its inputs are low. However, for any other combinations of inputs, the output will be low, as shown by the truth table. Logical expression for the same can be given as y is equals to I1 plus I2 whole complement. This is the NOR gate. And XOR gate. XOR gate is a OR gate. In these also we can see the inputs as I1 and I2, the output is Y. The truth table is the inputs I1 and I2, the output is Y. Here we can give the inputs as 0, 0, the output is 0. 0, 1, the output is also 1. 1, 0, the output is 1. And 1, 1, the output is also 0. XOR gate is a logical device which has its output high only when its inputs are having odd numbers of 1's complement as shown by the truth table. This means that the non-identical inputs results in a high output of the gate, while identical inputs bits cause the gate output to glow low. Logically, this is given by y is equals to I1 XNOR I2. Further, in its expanded form gets y is equals to I1 complement into I2 plus I1 into I2 complement. The gate is used as a parity checker and can have multiple inputs. And the next is XNOR gate. It is an even gate. Input is The inputs are I1 and I2 and output is Y. These can have the intermediate output. The truth table is inputs I1 and I2, intermediate output is M, the output is Y. Here the values are XNOR gate is a result of combining XNOR gate with a NOT gate, which means the output will be the inverted form of XOR outputs. Its output high only when its inputs are having even number as shown in the tutorial. This means that identical input bits results in high output of the gate. The identical input bits cause the output to go low. Logical expression for XNOR gate is given by y is equals to I1 XNOR I2 is equals to I1 XOR I2 whole complement is equals to I1 complement into I2 complement is plus I1 into I2. These also have and multiple inputs and serves as the parity checker. Finally, thank you.